Okay, let's have a look at an example. Now, this example is a little bit different. It's a good one to start with, but this is probably not the most common sort of question. It's a good one to start with, though, because it's easy. So just keep that in mind. You're probably not going to, in reality, get at such an easy question. Why is it easy? Because you're actually given the derivative. So we're given. So you don't even have to differentiate in this. Throughout this solution, all you have to be able to do is to substitute, to understand what a derivative function, what you can conclude from a derivative function, and be able to make conclusions, know what the different types of stationary points are. You know that much. Then the only maths that you find yourself doing is very simple substitution. Oh, hang on, and solve an equation. Okay, so given that the derivative is this, for what values of x does the function have a stationary point? And again, it seems to be slightly easy because they're only asking you for the value of x, whereas a much more common question is to actually find the stationary point, the whole point. Now, don't forget, a point, all points are denoted by a set of coordinates which has, so our answer would be, if we were giving a point, would not be just the x value, but an x and a y value. So that's a point, x and y value, whereas this question just says, what's the value of x? Complete a table of values identifying the sign of the derivative, so it's even telling you what you need to do, the sign of the derivative, either side of the stationary point, to determine its type. Now, you might get a question that just says, given a function, find the stationary point and determine its type or determine its nature. That's a much more common sort of question. Okay, but this is, like I said, it's a bit of a one-off. It's really easy. Lots of the steps have been taken out for you. So, to find the value of x, which is the question says, for what value of x? To find the value of x, or the x-ordinate would be just this part, and that's all this question's asking you to get. At a stationary point, we just solve first derivative equal to 0. So we're given the first derivative, 3 plus x, solve this little equation. It's not very difficult math skill here. We've got that it's going to happen when x is -3. We don't actually know what this function looks like. We know its derivative expression is this, but we don't know the actual function. Determine the type. To determine the type of the stationary point, complete the table below that establishes the gradient of the curve either side of the point. So it's all happening at -3, when x is -3. So I've chosen -4, and I've chosen 0. I could have chosen -2, I could have chosen -1, but I know that there aren't any other stationary points, because when I solved this I only got one value of x, so I can go as far away or as close as I like to x is 3 to test what's happening to the gradient. So when I put -4 into the gradient, then you can probably see that we're getting a -4, 3, where's our function for the gradient? 3 plus -4 is a negative. We know that if you put 3 in, you get a -3, you get a 0. What happens when you put 0 in? You get a positive. So what would a point look like if approaching it, you had negative gradient, at the point you had 0 gradient, and after it you've got a positive gradient? I think we can all see that would be a minimum. Therefore, the point is a minimum. I'll just pause the video and write up the solution to number 2. Example 2 is much more typical. So let's just get an understanding of what the question's about. It says the curve, and you're given the actual function or the y values for the curve, x cubed minus 6x squared plus 5 has 2 turning points. Now, some of this should be rather familiar. We know that a cubic, remember I've said a cubic basically just has, I suppose there are four different shapes, and they could be, let me choose a pretty colour, they could be, a cubic could be this shape, or the reverse of that, which is that one, and have 2 turning points, 1, 2, 1, 2, or a cubic could be the basic cubic you might know with just the 1 turning point, or that one. Now, cubics won't be anything other than a variation of those 4 shapes. And what you will learn is that if the number in front of the x cubed is positive, this one's the positive. Why? Because as we go to infinity, it's getting bigger and bigger and bigger, positive. If the number in front of the x cubed, if there's a negative in front of the x cubed, it'll be this one. So this one is negative. And these don't have x's and x squareds. Okay, so we can take the time, look at the detail of the question and go, yeah, well, I would know that because it's a cubic, it's a bit complicated, it's got x squareds in it, and it's got a constant. Yeah, it would have 2 turning points. It says, find them. So we're finding 2 points. Don't forget, each point will be in the form x and y, and we use the derivative then to distinguish their nature. Find them and use the derivative to distinguish their nature. I think I might have left out a bracket there. So find them and use the derivative to decide whether they are maximums or minimums. You almost certainly know that the first turning point you come to should really be a maximum, and the second one should be a minimum. So it's always great if you've got an understanding of what your answer should be from the beginning. Of course, we don't know we can't look at this and there's nothing about it that I can say, oh, and we know that the turning points will occur at this x value and that x value. Not generally from this point, but we know how to get those x values, so that's what we would then do. It says to find the x value of a stationary point, you solve the first derivative equals 0. So your first derivative will be an expression in x. You solve an expression in x, you're finding the value of x, you're finding the x values of a point that will then establish as a stationary point. So this is our function, this is our derivative, solve it equal to 0, and we get 2 x values, 0 and 4. Please stop the video at any time if you want to rewrite this out yourself and take it a little bit more slowly. You'll have the option to do that. Just pause the video, write down your solution and have a think about what you've written. So we know there are 2 stationary points. We don't know what they are yet, but we've got a pretty good idea that at 0 we should get a maximum because we know that we're going to get something of this shape. And at 4 we should get a minimum. It says use the derivative to distinguish their nature, so that's what we have to do. Actually, we're not quite finished. We haven't found the entire point. So we will, at x is equal to 0, though, we'll be finding the y value. So remember, y is the same as function. And if I sub 0 into here, clearly you get y. So 1 stationary point at 0, 5. Sorry. And then at x is equal to 4, sub 4 in, because this gives us the y or f of x. Sorry. And if I haven't made a mistake, then you get y is minus 27. So now I do have my 2 points completed. So I've done this, I've found them, the 2 points. To distinguish the nature, investigate gradients. So we'd first investigate at x is equal to 0, and our second one will be, oh, whoops, why did I do that? At x is equal to 4, let's change that 5 to a 4. It's not going to make any difference in the calculation. But at x is equal to 0, now I've chosen a minus 1 and a 2, just to keep them whole numbers. When I sub, I'm investigating the gradient. This is where some students get caught out and they actually substitute this back into the original function. But remember, we only sub into the original function when you want the y value. I'm not investigating y values, I'm investigating the gradient, so I sub into the first derivative. This is the expression for the first derivative, and I get a positive number. We know at 0, the gradient's 0, so that's what established it as a stationary point. To investigate it, and at 2 I get a negative. So if I was going positive, then 0, then negative, you can probably see, yes, that is a maximum. Likewise, at x is equal to 4, should be a 4. Then I've gone back down to 2. I didn't go 3 because I would have had to do another calculation. It's fine to go to 2. I know the gradient of 2 is a negative. Nothing's happening between 2 and 4. At 4, the gradient's 0. At 6, when I sub into here, I get a negative. Whoops. Okay. I'm not sure what I had there, but at x is equal to 4, x is equal to 4, we're going either side. When we sub 2 in, we get a negative, so the gradient is negative, then it's 0, and then it's a positive, and you can see this is a minimum. So what would our graph actually look like? So we know we're going to go through this point 0, 5. Oops, sorry, and we're going to go through 5, negative 27. That's going to be a minimum, and here we're going to have a maximum. So we're going to come up. This is going to be a max. Whoops. Not sure really where it's cutting. It's not intentional that I'm cutting it anywhere, because I haven't worked out the intercepts, the x-intercepts. We're coming across to negative 27, and I know I'm going up. So I don't know actually what that value and that value of the x-intercepts are, but the graph would look like that, which is what we expected. I think that's it, and you'll be right to do the homework you do.